Hello all, this is Dr. T. Thirupal from G. Pillai College of Engineering and Technology, working as a professor in the Department of Electronics and Communication Engineering. Now, I am going to deal about the GATE subject, which is called as electronic devices, So, coming to GATE, which is a very important for electronics and communication engineering students, and this GATE stands for Graduate Aptitude Test in Engineering. And especially this GATE, it's very useful for ECE students where they can grab many opportunities in core companies, or they can go for higher studies like MTech. They can do MS with a scholarship amount of 25 to 50K. And here, let us go with deep into the subject called electronic devices. First, let us have the broad description about the syllabus of electronic devices in the GATE examinations. Now we have it's been divided into three topics, which is called semiconductor physics, diodes, and transistors. And semiconductor physics, it's been carried by 4 marks, and diodes, which is carried for 3 marks, and transistors containing BJTs and MOSFETs, it's been carried for 3 marks. So here the syllabus has been divided into 3 parts actually, because for making the students to learn easy and to grab more amount of marks in electronic devices, we have been split into 3 parts. Here this is a 3 part semiconductor physics, where it is been contained by energy bands, carrier concentration, direct and indirect band gaps, drift, mobility, generation, recombination, Poisson and continuity equations. Likewise, even diodes, PN junction diode, we learn what special diodes called GNA diode, LED, light emitting diode, photodiode, and solar cell. And coming to transistors, we have BJTs and metal oxide semiconductor field effect transistors. In that, the main important part is mass capacitor we will be learning over here, right? So now let us go deep into the subject, which is called semiconductor physics. Under this, the first topic we would like to learn is the atomic structure. Let us learn about this atomic structure, and let us have some glance of GATE questions in this atomic structure, right? So first, as you know that atom is a combination of protons plus neutrons plus electrons. And as you see this, protons plus neutrons is nothing but a nucleus. So here I can say that nucleus is a combination of protons plus neutrons, and this nucleus is always a positively charged particle. It is a positively charged particle. As you see this, because it's been combined with a proton, which is a positively charged particle, and a neutron, which is a neutral one. So therefore, the combination of proton plus neutron is nothing but a positively charged particle. For example, if nucleus has been combined with neutrons plus electrons, then it is a negatively charged particle, because electron is always a negatively charged particle. But here we are taking into consideration protons plus neutrons, which is called as a nucleus, and this nucleus is nothing but a positively charged particle. Around this nucleus, there are certain electrons which are revolving around the nucleus, where you can see these are the electrons which are revolving in respective orbits. This is called as a first orbit, or it is also called as a first shell. It is called as a first orbit or first shell, where the electrons are revolving around the nucleus. It is called as a first orbit or first shell. And in this, how many electrons are revolving around the nucleus in first orbit? Those are nothing but example, there are 2 electrons which are revolving around the nucleus in first orbit. And similarly, as you move farther away from this nucleus, you have second orbit here. This second orbit or second shell, which is contained by again electrons revolving around the nucleus. So how many electrons are there revolving around the nucleus in second orbit? Means again it is nothing but 8 electrons revolving around the nucleus in second orbit. So likewise, I can say that here, as you move farther away from this nucleus, the energy possessed by each orbit goes on increases, because here the energy possessed by the electrons present in first orbit are only 2. So therefore, you can take, for example, it's a 2 joules of energy which is contained in first orbit. Similarly, 8 joules of energy which is contained in second orbit. Likewise, if you move to third orbit here, as you move farther away from the nucleus, you have third orbit or third shell, where it is contained by 18 electrons. So therefore 18 joules of energy, for example, it's present in third orbit. So therefore, as you move further away from the nucleus, energy possessed by the orbit goes on increases. So as you go like this, you have a last shell which is called as a valency shell. This is called as a valency orbit or valency shell, because valency electrons are revolving around the nucleus at outermost orbit. So therefore, it is called as a valency shell or valency orbit. Now here, the most important questions that comes in gate examinations regarding this is the first question: number of electrons revolving around the nucleus. Number of electrons present in each orbit. Number of electrons present in each orbit is given by a formula called 2n square. 2n square, where n is nothing but the number of orbitals. N represents number of orbitals. For example, if n is equal to 1, n is equal to 1 represents a first orbit. N is equal to 1 represents, it is representing as a first orbit. First orbit, how many electrons means 2 into 1 square, that is equal to 2 electrons. 2 electrons are present in first orbit. N is equal to 2. N is equal to 2 means it is a second orbit. So second orbit means how many electrons? 2 into 2 square, 4 into 8. 8 electrons are revolving around the nucleus in second orbit. Similarly, N is equal to 3. If N is equal to 3, then it is called third orbit or third shell, where it is nothing but 2 into 3 square, 9, 9 into 2, 18. 18 electrons are revolving around the nucleus in third orbit. Likewise, as you move further away from the nucleus, for example, if you move like this, you can take N is equal to 5, fifth orbit. Then fifth orbit or fifth shell, the number of electrons are 2 into 5 square. 50 electrons are present. 50 electrons are revolving around the nucleus in fifth orbit. So likewise, you can able to calculate the number of electrons revolving around the nucleus in each orbit. So this is the most important point regarding number of electrons revolving around the nucleus in each orbital. Next, coming to second point, most important point, energy possessed by the orbitals. Energy possessed by the orbitals. Energy possessed by each orbit. For example, the first orbit. What is the energy possessed by first orbit? It's nothing but, if you consider it as E1, which is nothing but E1 is equal to how many energy? It's nothing but 2 joules of energy. Suppose if you consider second orbit E2, that is equal to 8 joules of energy. For example, it's just for example, we are taking each electron is possessed by 1 joule of energy. Then you can take E1 2 joules, E2 8 joules, then E3, then it's nothing but 18 joules. Likewise, if you go for the last orbit, the energy level increases. So therefore, you can have a concept like this here. Suppose if I have E1 is the first energy level, E2 is the second energy level, E3 is the third energy level, E4 is the fourth energy level. Likewise, the last energy level E5, E last energy level as EL. Then you can have a relation here like this: E1 is less than E2, E2 is less than E3, E3 is less than E4, and the last energy is always greater than the before energy level. Right. The next third important point that we need to consider over here is the attraction forces of the electrons revolving around the nucleus. The attraction forces. The attraction forces, if you consider here, for example, the electrons revolving in first orbit. What is the attraction force of the electrons revolving in first orbit? Here, if you consider this is the electron, it is more attracted towards the nucleus because it is very nearer to the nucleus. Consider here electrons revolving in second orbit. They are loosely bound to the nucleus because they are farther away from the nucleus compared to first orbit. Likewise, third orbit, it is loosely bound. Likewise, last orbit, it is completely loosely bound. So therefore, I can say that here if you consider attraction force of first orbit as AF1, attraction force of second orbit as AF2, attraction force of third orbit as AF3 dash dash dash, attraction force of last orbit as AFL, then attraction force of first orbit is always very much attracted towards the nucleus compared to second orbit, similarly compared to third orbit, similarly compared to fourth orbit, compared to last orbit. So therefore, these are the most important points that comes into consideration in gate examinations. Now let us see the last orbit comes here, the valency orbit, where the valency electrons are revolving around the nucleus. Now if you consider here, how does the current flow in this semiconductor devices? Let us see how does current flows in this semiconductor devices. Right, let us see how does current flows in semiconductors using this atomic structure. As you see here, the atomic structure is a combination of nucleus, electrons and protons. And protons plus neutrons is nothing but a nucleus, and electrons are revolving around the nucleus in different orbitals. Now here, as you see here, as you move farther away from the nucleus, you have a last valency orbit where valency electrons are revolving around the nucleus. Okay, here you can consider here, even if you see, each orbital is also a combination of subshells, because this is called as a shell 1, this is called shell 2, likewise you go for shell 3, shell 4, and this is last shell, this is called last shell or valency shell. Now here in this each shell, which is called as an orbit, each shell is contained by subshells, where the subshells are called as a SPDF, where electrons are present in this SPDF, which are called as subshells. Suppose if it is S subshell, how many electrons are maximum will be present in this S subshell is 2 electrons will be present in S subshell. And if it is P subshell, then 6 electrons will be present. If it is D, 10 electrons it is been occupied. And if it is F, 14 electrons will be present in this subshell. For example, I have an element called as carbon. Suppose if you take a carbon element where its atomic number is 6, then you can write 6 as like this. Its configuration is written as 1s square, 2s square, because 1s, only S is contained by 2 electrons. And in the second cell again it is contained by S and P. So again first S is contained by 2 electrons and the next P is contained by 2 electrons. It is 1s square, 2s square, 2p6. So therefore here 2 electrons, 2 electrons, 2 electrons. So totally 6 electrons will be present in the subshells. So it's a combination of a carbon which is an atomic number is 6. Now let us go with how does current flows in this atomic structure. As you see, as I told, it's electrons are present at outermost orbit which are carried with a negative charge. So this is the electron which is loosely bound to the nucleus, because it is farther away from the nucleus, so therefore it is loosely bound to the nucleus. So therefore if any energy, external energy is being given to this electron, what happens is this electron immediately takes energy from external source. It may be sunlight or it may be external energy. Then this electron bounce back and then becomes a free electron. This is called as a free electron. It is becoming a free because it's not been attracted by any nucleus here. So therefore it is becoming a free electron. Now this free electron searches for another hole in the atmosphere. For example, another atom is present which is contained by nucleus here, and the first orbital, second orbital or third orbital. Suppose if a hole is present here, this electron which is becoming a free electron from this atomic structure, it checks for searches for another hole here. Therefore this electron fill into this hole here, leaving again a hole here, because this electron jumps and fill this hole, therefore leaving again a hole here. Again this electron takes energy from external source, again becomes a free electron, leaving here again a hole here. So likewise again this electron jumps to another valence electron. If it finds a hole, then again it fills this hole, leaving here hole. Likewise, again it jumps, again finds a hole, then fill into this hole, leaving here hole. So likewise, electron keeps on jumping for another holes present in the atmosphere. So if you see here, this is a continuous process which has been happening in the atmosphere. So therefore here, if electron is jumping from left to right, continuously you can observe here, it has been jumping from left to right. So therefore, a continuous current flow will be happen. That current is called electron current. So this current is called electron current, which has been continuously flowing. And you can see the holes which are moving from right towards left, because it is leaving a hole here, here hole, here hole, here hole, here hole. So therefore, holes direction is from right to left, and even holes are also continuously moving. So therefore, it is creating a current. That current is called as a hole current. So total current existing here in this atomic structure is given by total current is equal to electron current plus hole current. So this is how the current is generated in atomic structures with the help of the electrons revolving at outermost orbit, right? So now let's go with another topic where just now we have seen the subcells SPDF, and the electrons have been occupied in this subcells. Yes, you can see here only 2 electrons. Again in nth cell, again 2 electrons in S, 6 in P. Again mth cell 2, 6, 10. D is occupied by 10 and F is occupied by 14. Right? Next, we'll go with the energy bands here. What is this energy band actually? The combination of energies of all electrons revolving around the nucleus. Or if you consider each orbit, there are different electrons revolving in each orbit. If you combine all the energies of electrons in each orbit, then it forms a band. That band is called energy band, because you are merging the energies of all the electrons revolving around the orbit. So therefore, here, for example, if you take first orbit, it contains only 2 electrons. So 2 electrons, for example, each electron is being occupied by 1 joule of energy. Then if you combine these 1 joule plus 1 joule, then you get 2 joules of energy. So therefore, total energy possessed by the first orbit is 2 joules of energy. So this 2 joules of energy is called as an energy band. So energy band is nothing but a combining of energies of all the electrons revolving in respective orbit is called as an energy band. So for example, if you see here, the first band, it is contained by 2 joules of energy here. So therefore, it is very nearer to the edge of the nucleus. If you consider this one is edge of the nucleus, then the 2 joules of energy is very nearer to the edge of the nucleus. For example, second orbit, it is contained by 8 electrons. So 8 electrons means 8 joules of energy. For example, 8 joules of energy. So therefore, 8 joules is above than 2 joules. So combining all this electrons energies, it will form 8 joules. And third energy band, it is nothing but 18 joules. It is present in the topmost of again second orbit. So therefore, likewise, if you go and combine all the energies of electrons revolving in valency orbit, then it can be formed as a valency band, because all the valencies electrons, if you combine energies, then it will form a valency band. So therefore, as you move like this, then it will form a valency band, and this valency band is given by EV, where V stands for valency and E stands for energy, valency band. For example, electron is present here. If I give some external energy, then this electron jumps and enters into conduction band, because it is the electron which is responsible for flow of electrons current. So therefore, it is present in a band called conduction band. So therefore, if you merge all the free electrons energies, then it will form again in a band. That band is called as a conduction band. So therefore, conduction band is always greater than valency energy band. You can see here, valency energy band is here, and if you combine all the energies of electrons present in a free state, then it will form a conduction band. So therefore, it is given by EC. So therefore, the gap between conduction band and valency band is nothing but called as forbidden energy gap. It is called as forbidden energy gap or energy gap. and it is given by Eg. It is given by Eg. For example, here now, if you see here, the energy gap is very, very large here. Energy gap is very, very large, and even this one can be given by Eg, and it is equal to highest energy level Ec minus Ev, valence energy level Ev. Eg is equal to Ec minus Ev. So this energy level is very, very large here. Large means it is approximately equal to how much? It is approximately equal to 6 electron volts. For example, it is approximately equal to 6 electron volts. If it is equal to 6 electron volts, then in semiconductors, it's very difficult to obtain 6 electron volts of energy. So therefore the device becomes non-conducting. That means the device is non-conducting means it is called as an insulator. So I can say that here energy gap is approximately equal to 6 electron volts, then the device is called as an insulator. For example, what are the examples where energy gap is having a 6 electron volts? Means it is nothing but carbon and graphite, sorry, diamond, wood. These are all the examples. Plastic. These are all the examples of semiconductor insulators where their energy gap is equal to 6 electron volts. Right? Now coming to the energy gap, I have been reduced this energy gap here. Here it is very large. Now I have been reduced to small quantity. That means here the energy gap is approximately equal to 1 electron volt. So this 1 electron volt in semiconductors, we can acquire this energy, right, by with respect to some external energy sources or with respect to sunlight, we can able to acquire this energy gap. So if you want to acquire this energy gap, means acquiring this energy gap means electron present in valency orbit definitely enters into conduction band, in turn creates a current flow. But with respect to some external energy which is been applied to that electron which is present in valency band. So now here this type of devices whose energy gap is approximately equal to 1 electron volt, those devices are called semiconductors. So the name itself tells you semiconductor, where its conductivity lies in between insulator and conductor. So it is a half conduction takes place, because at 0 degree Kelvin, even nothing energy I am giving. So at 0 degree Kelvin, all semiconductors acts like insulators. All semiconductors acts like insulators, because there is nothing energy which is being given to this, right? So here, so therefore, for all the semiconductors, energy gap is approximately equal to 1 electron volt, because we can acquire this energy gap in semiconductors. There are basic examples of semiconductors like single crystal semiconductor and compound crystal semiconductor. Single crystal semiconductors examples are silicon and germanium. It's a single crystal semiconductor. And compound crystal semiconductors, even we can go for compound crystal semiconductors also. For example, it's a combination of two materials which is called gallium and arsenide, or gallium nitride, or gallium phosphide, or gallium arsenide phosphide. These are all the compound crystal semiconductors where two or more materials are used to form a semiconductor, right? Now consider these semiconductors. I can say these semiconductors are negative temperature coefficients. Why they are called negative temperature coefficients? We will see here in this case. These are called negative temperature coefficients. All semiconductors are called negative temperature coefficients, because as these possess energy gap is equal to 1 electron volt. So this energy gap can be acquired by the devices. So therefore here as temperature rises, then what happens is conductivity increases. As temperature rises, conductivity of the charge carriers increases. If conductivity increases, what about resistivity? Resistivity decreases. As conductivity increases, resistivity decreases. So therefore, so temperature rises, if you consider here a temperature and here a resistivity, temperature and resistivity. So as temperature is increasing, what about this resistance? At a temperature is equal to 0 degree Kelvin, you have highest resistivity, so therefore it decreases like this, like this. This is called as negative temperature coefficient, because conductivity has been increasing and resistivity has been decreasing as temperature increases. So all semiconductors possess negative temperature coefficients, right? Next, you go with again still decrement of the energy gap which is present in between valence band and conduction band. Still we have decreased from 6 electron volts to 1 electron volts here, and then from 1 electron volts to 0 electron volts. Here I can consider here Eg is approximately equal to 0 electron volts. If it is 0 electron volts, then there is no gap, energy gap between conduction band and valence band. So therefore at that time what happens? Energy conduction band and valence band will get overlap. Overlap means here this is from this point to this point it is conduction band, and from this point to this point it is valence band, this point to this point. But here from this point to this point it is conduction band, so both are overlapped. So the electrons present in valence band are already existing in conduction band. So there is no need to give external energy for the electron which is present in valence band to jump into conduction band. It's already been taken there because it's been overlapped, because there is no energy gap. Energy gap is equal to 0 we are maintaining. So therefore what happens is all conductors possess energy gap is equal to 0 electron volts. No external energy is required. For example, all metals are called conductors. All metals are called conductors. And all, for example, a natural example is iron. Iron is the best example of a conductor, because there is no even a threshold point also. There is no even a threshold point. Definitely, just if you give a light energy, immediately current is flown in the device, and that has been observed in conductors devices. And now this conductors, I can say that these conductors are possessed by positive temperature coefficients. What is this positive temperature coefficient? Because as temperature increases, the vibration pattern, because there is no gap, because it's been overlapped, it's been filled already with electrons. So there is no gap of electron to move in the device. So therefore, as temperature increases, vibration pattern, vibration of charge carriers decreases. Vibration of charge carriers decreases. If vibration of charge carriers decreases, what happens? Conductivity decrease, because there is no moment. There is no moment of charge carrier, so therefore conductivity decrease. If conductivity decreases, what about resistivity? Resistivity increases. Resistivity increases. So therefore, I can say that here, as I take here temperature on x-axis and resistivity on y-axis, then as temperature is increased, what happens is resistivity also increases. Resistivity also increases. This is called as positive temperature coefficient. This is called positive temperature coefficient. As temperature increases, vibration of charge carriers decreases, conductivity decreases, and therefore resistivity increases. So all conductors possess a positive temperature coefficients. Right? Now here, one important point we need to learn here is, what is the forbidden energy gap of silicon and germanium at T is equal to 0 degree Kelvin? I can say that here in semiconductor, I told you here we have a valency energy band, and here we have a conduction energy band EC, and the energy gap between EV and EC is called forbidden energy gap, and this is approximately equal to 1 electron volt for semiconductor. Now this energy gap depends on temperature. So energy gap depends on temperature. As temperature increases, definitely energy gap decreases. energy gap decreases. Because the simple reason, if electrons are present in valence band, if temperature is been applied here, which is nothing but energy, so therefore electron jumps from valence band to conduction band, where the energy levels are been occupied in conduction band. So therefore energy gap decreases. So I can say that as temperature is increased, energy gap decreases here. But how much is the quantity that is been decreased for silicon and germanium, where it's very important for gate examinations here, right? Now here I can say that for every 1 degree Kelvin, rise of temperature, silicon material energy gap decays by 3.6 into 10 power minus 4 electron volts per degree Kelvin. That means for every 1 degree Kelvin rise in temperature, silicon materials, its energy gap decays by 3.6 into 10 power minus 4 electron volts. And similarly, for germanium material, energy gap decreases by 2.23 into 10 power minus 4 electron volts per degree Kelvin. Okay. Now, for example, silicon materials, I have here its energy gap as energy gap is equal to 1.21 minus 3.6 into 10 power minus 4 into capital T. 1.21 electron volts minus 3.6 into 10 power minus 4 into capital T. For example, T is equal to 0 degree Kelvin, then energy gap is equal to 1.21 minus 3.6 into 10 power minus 4 into 0. So that is equal to, I will get energy gap is equal to 1.21 electron volts at 0 degree Kelvin. For example, at room temperature, T is equal to 27 degrees C, room temperature plus 273, if we want to convert into kelvins, that is equal to 300 degree Kelvin. So therefore Eg is equal to 1.21 minus 3.6 into 10 power minus 4 into 300. So you get approximately is equal to 1.1 electron volts. 1.1 electron volts. So this is a very, very, very important concept, where at T is equal to 300 degree Kelvin, Eg is equal to 1.21 minus 3.6 into 10 power minus 4 into 300. So you get energy gap 1.1 electron volts. So from these 2 points, I can say that as temperature is raised, energy gap is being decreased. If energy gap is decreased, then conductivity increases. Conductivity increases, resistivity decays. As conductivity and resistivity are inversely proportional, so it decays. This is for the concept of silicon material. Let us check for the concept of germanium material here. For example, germanium material, what happens? See, germanium material, if it is a germanium material, then what is the energy gap? It is given by energy gap is equal to 0.785 electron volts, 0.785 electron volts. Energy gap is equal to 0.785 electron volts minus, per every degree Kelvin rise, its energy gap for germanium decays by 2.23 into 10 power minus 4 electron volts into capital T. So the formula to calculate energy gap for germanium is 0.785 minus 2.23 into 10 power minus 4 into capital T. Now let us check for 0 degree Kelvin here. At T is equal to 0 degree Kelvin, case 1, we get energy gap for germanium as 0.785 minus 2.23 into 10 power minus 4 into 0. So you get energy gap is equal to 0.785 electron volts. Energy gap is equal to 0.785 electron volts. This is exclusively for germanium material. Similarly, at T is equal to room temperature, T is equal to room temperature is given by 27 degrees C. 27 degrees C, convert into kelvins, that is 27 plus 273, then you get a temperature T is equal to 300 degree Kelvin. So therefore, you get energy gap is equal to 0.785 minus 2.23 into 10 power minus 4 into 300. So you get energy gap is equal to 0.72 electron volts. Even for germanium case also, we can able to tell that as temperature rises, energy gap decays and conductivity increases and resistivity decays. This is what the concept of energy gap, forbidden energy gap of silicon and germanium at room temperature and also at 0 degree Kelvin. The same thing you can even apply for 500 degree Kelvin also. 500 degree Kelvin. The same example for germanium 500 degree Kelvin, Eg is equal to 0.785 minus 2.23 into 10 power minus 4 into 500. Capital T is equal to 500 because 500 degree Kelvin means T is equal to 500. 500 means substitute T value as 500. So you get 0.785 minus 2.23 into 10 power minus 4. This is for germanium case. And similarly for silicon, at T is equal to 500, energy gap is equal to 1.21 minus 3.6 into 10 power minus 4 into 500. So you get for silicon case. As you see here, it has been decreased here definitely, and it has been decreased here, its energy gap, right? So these are the most important concepts of semiconductor physics, that is regarding a germanium material, regarding silicon material, and regarding gallium arsenide material also, right? Now you can have why silicon material is the best used material in semiconductors. This is also a very important concept here. I have here germanium material, silicon, gallium and arsenide materials. Now here you can see here germanium material, its atomic number is 32. Germanium atomic number is 32, whereas silicon, its atomic number is 14. Atomic number is 14. And wherever you can see here silicon material, its orbitals are only 3. This is atomic number. Orbitals, silicon orbitals are only 3. This is 1, 2, 3. But whereas germanium, how many orbitals? 4 orbitals are present here. Because first orbital is contained by how many? 2 electrons. Second orbital is contained by 8 electrons. Third orbital is 18 electrons. And remaining for 32, the fourth electron is contained by 4 electrons here. Similarly for silicon here, first orbit is 2 electrons, second orbit is 8 electrons, and 4 electrons are present at a valency orbit. Okay. So if any material which is occupied with 4 electrons at outermost orbit, then it is called as tetravalent atom. 4 electrons at outermost orbit. 4 electrons at outermost orbit, then it is called tetravalent atom. Similarly, if 3 electrons at outermost orbit, then it is called trivalent atom. Similarly, if 5 electrons are present at outermost orbit, then it is called pentavalent atom. These are the 3 most important points to be remembered 4 electrons are there at outermost orbit, then it is called tetravalent, 3 electrons trivalent, 5 electrons pentavalent. Now here for germanium and silicon, which are called single crystal semiconductors, we have only 4 electrons outermost orbit here and 4 electrons at outermost orbit here. So it is called as a tetravalent material here. Here only 3 orbitals, here only 4 orbitals. Now we know the concept here, stability here. What is that stability here? If I apply the same joules of energy for both germanium and silicon, same, for example, if I apply 1 joule of energy, for 1 joule of energy, the outermost electrons here, they are very much bounded to the nucleus, and here loosely bounded to the nucleus. So therefore, electrons present in germanium material will comes outside first compared to that of silicon material. So as temperature increases, energy increases, if I apply more energy to the outermost orbit, what happens is germanium becomes unstable because all electrons comes outside. But silicon material, only few electrons comes outside because it is more attracted towards the nucleus. So therefore, silicon material is stable, and whereas germanium material is unstable. What is stability actually? For every bounded input, we need to produce unbounded output only. That is called as stability. But whereas silicon material here, only for bounded input of energy, it is producing bounded output of electrons. But here in germanium material, if I give bounded input, you get unbounded output, which is called as unstable in nature, right? Whereas germanium material, it has been introduced in the year 1947. Whereas here silicon material, it is introduced in the year 1954. Germanium material, it is abundantly available on Earth surface. Abundantly available on Earth surface. Even silicon material also abundantly available on Earth surface in the form of sand. You can see sand. But here purification cost is less. Germanium material can be purified with less cost. Purification cost is less, but whereas purification cost is very high for silicon material. If you want to get a pure silicon material, its cost is very, very high. Purification cost is very high. But even though purification cost is high, it is stable. So that's why it is best to use the semiconductor in electronics and communications and in electronic devices, right? And another atom which is coming into existence, which is called as gallium arsenide atom, which is a combination of two materials, which is gallium and arsenide. Gallium is a combination of atomic number is 31 and arsenide is atomic number is 33, which is a new material which has been introduced in atmosphere here, which is called as compound crystal semiconductor, gallium arsenide. As you consider into speed into consideration, gallium arsenide is 5 times faster than silicon material. And the raw material is not abundantly available on Earth's surface here, because gallium arsenide we need to import it from other countries, so therefore it is not abundantly available on Earth's surface. It is not abundantly available on Earth's surface. And it is found in the year 1970s. It is found in the years 1970s. But it is the main advantage is it is 5 times faster than silicon. But the material is not abundantly available on Earth's surface. Even if it is available, even if we import from other countries, then we need to purify it. That purification cost is very high. Purification cost is very high. Purification cost is very high. So these are the basic differences between germanium, silicon and gallium arsenide. So out of these three, the silicon material is the best used material in electronics. Thank you so much, and we'll start in continue in the next class. Thank you.